Hi, I'm Val, and I'll be presenting our work on measuring the costs of planning. Different biases in planning have been extensively documented. For example, the bias to pay more attention to the present than the future, which is called the present bias, or the bias to not plan at all. One hypothesis is that these biases may arise from different cognitive costs for planning or planning into the future. In this work, we present a method to infer these individual differences using Bayesian inverse reinforcement learning and validate it with simulations in an experiment. We use a planning task called the web of cash. In this task, the participant is told that they are guiding a money-loving spider through a web of cash. Each node the spider lands on contains either a monetary gain or loss. The nodes begin covered, and participants are told that they can click on nodes to reveal the values behind them if they want, before they start to move the spider. However, revealing a node incurs a $1 fee. You can see the distribution of values behind each type of node. The nodes that are further out, in blue, have more variance than the inner nodes and are therefore more informative when selecting a path. People with present bias may inspect the inside nodes even when they don't provide as much information. In order to infer the cognitive costs experienced by participants, we need a generative model of how they select actions. For this, we use a meta-level Markov decision process, or MDP. MDPs consist of four important components: states, actions, transition matrix, and rewards. Here, a state encodes which locations have been inspected and what the payoffs behind the nodes are. The actions are the cognitive operations of planning that are operationalized as either clicking on a node to uncover it or choosing to finish the planning phase. The transition probabilities from one belief state to the next are all 1/4, since there are 4 possible node values a participant might uncover. If the participant chooses to end the inspection phase, the probability will be 1 that the phase will end. The rewards here are the cost for taking a planning operation, or if choosing to terminate the planning phase, the maximum expected path value. In past work, the cost of a planning operation has been taken to be the $1 fee people are instructed on. We will introduce a parameterized reward function in order to uncover individual differences and experience cognitive costs. We considered 4 models of reward and action selection. These models parameterize the cost of a planning operation in terms of 2 components: a static cost, that is the same for all planning operations, and a depth cost that increases linearly with the number of steps that the planning operation looks into the future. The full model shown in the first row includes both of these parameters, linear depth and static cost. A participant with a higher linear depth weight might prefer to click on nodes closer to the start of the web. A participant with a higher static cost weight might prefer not to plan at all, as it would be too costly. With these reward functions, we can find the optimal state action value functions for an agent using dynamic programming to solve the MDP. The resulting values quantify the long-term value of taking any action in any state. We then add softmax action selection over these value functions. This means that an agent won't always take the action with the best value in a state, but will take each action proportionate to its long-term value. Using participant data, we tested the maximal model with both parameters against nested models with less parameters and found that it had the best Bayesian information criterion, which penalizes models for the number of parameters. You can see this in the BIC column, where lower is better. We will use Bayesian inverse reinforcement learning to infer the reward function parameter weights by inverting the generative model I just described. Bayesian inverse reinforcement learning gives us the weights of a reward function given an observed trajectory of clicks tau. We next simulated many trajectories with different ground truth parameter combinations. We found that static cost and depth were recovered well. There was some correlation between the 2 parameters, and static cost was recovered a little higher than what it truly was. Next, we classified the planning strategies of participants using the computational microscope developed in our lab. Participants exhibiting present bias or no planning bias have a higher inferred depth cost, as one might expect. To validate that our method measures the cost of planning, we experimentally manipulated the cost of planning and applied our method to the resulting click sequences of 116 participants. We gave each participant a new set of cost parameters drawn from a grid and tried to recover the given cost parameters. We aimed to show that the difference is recoverable. For example, we should infer a higher depth cost for people given a higher instructed depth cost. We performed 2 linear regressions. The instructed cost weights were used as predictors in both regressions. The dependent variable was either the inferred depth cost weight or the inferred static cost weight. We found that the inferences of our method were accurate for experimentally induced differences in depth cost and static costs across participants. So, to summarize our work, we leveraged Bayesian inverse reinforcement learning to measure individual differences in the subjective costs of planning. Our results highlight developing and testing personalized interventions and diagnostic applications for individuals exhibiting biased behavior in planning tasks. Thanks for listening. If you're interested in learning more, please don't hesitate to get in touch.